Alright, so the steps for the substitution method, and I think you guys might like this better than you did the elimination method. But the steps are, first of all, and that equation like we were looking at a few minutes ago, that we already have one variable solved for. So that very first equation we've got today is very, very simple. But you take one of your equations and you solve for x or y. So if I was to take a linear equation, I'm to solve it for y, what form did I just put it in? If I solved it for y, got y by itself. What form is that in? Y'all remember? If I take a linear equation, now we've talked about this for 9 weeks.
And we've been out for one of those.
Yeah, we've been out for one. So 10. Okay, I'm not counting going around. So if I take a linear equation and I get y by itself, y equal 2x plus 3. What form? I've got it in slope-intercept form. I've got it in y equal mx plus b form. If I put x by itself, I've just got x by itself. But either one, and it says either one, so that means it doesn't matter, right? Doesn't matter. So which one should you pick? Hey, whichever one's the easiest. Or easier. Whichever one's easier. Alright, number 2, plug in what you found into the second equation. That's important. Don't plug the equation you solved for back into itself. You always get a consistent dependent system. So take the equation you solve for x or y, and if you solve for y, I'll just use that for an example. If I solve for y, I'm going to plug into the second equation in for what? Y. That's what I solved for, okay? Number 3, solve the new equation for the variable. Once I get it all plugged in, I've formed a new equation. I'm going to have 2 variables, and I'm going to solve for it, but they're both going to be the same. If I've solved for y, they're both going to be y's. If I've solved for x, they're both going to be x's. So whatever variable I've got, I solve for that. And then take number 4, what you found for x or y, plug it into either, or really, since the solution should work for both, plug it in for both original equations to find the other variable. Now once I've got my ordered pair, I check the solution in both equations, make sure it works. If I graphed this solution, this would be the point where they did what? Crossed or intersected. Okay. But as we know, there are 2 other types of systems. There are systems where the lines are parallel, which means we've got an inconsistent system and no solution. Do you remember that? Or we've got coinciding lines, one line on top of the other. Actually, it's the same line twice. And that's an infinite set of ordered pairs because every point on that line is now a solution. And what do I call that? Consistent, dependent. If you've got one line on itself. Alright, so what's going to happen there is number 6. Just like in the elimination method, if both variables cancel, the solution is no solution with the false statement or an infinite set with the true statement. And we'll get to that, but we're going to work the consistent independent types first. Alright, now this is the simplest type of substitution property or substitution method that there is because I already know that x is 3. I already know, since this other line is not horizontal and it's not vertical, that this vertical line in number 2 is going to intersect this line. So I already know I have a consistent independent system and x is 3. So I think you were saying earlier this looks a whole lot like the second half of the elimination method, and that's when you have a vertical or horizontal line. That's kind of a special case. So take this x is 3 and substitute it in right there, guys, and let's solve for y. So we're going to plug in x is 3. Multiply. Subtract. Why do you think that this method or the elimination method would be better than the graphing method? Where did I get here? I got a decimal or a fraction. Those are hard to graph with, aren't they? Remember, we talked about earlier that this x-intercept would be 19/8. 2 3/8. And this would be a y-intercept would be 9.5. And so that line would be tough to graph anyway. And so an algebraic method, substitution or elimination, makes it easier. Alright, what about this? Here's a second example for us. Now step 1 here has already been finished, because I've already got y by itself right here. I don't have to find it, I don't have to make it true. It's already there. So when I look at the steps that you have written, and it says solve for a variable for x or y, and then plug what you found into the other equation. Okay? So here it is. And into this other equation, just like subbing into a ball game, right? I'm going to take this player out. This y is coming out. And this amount is going in. So I've solved for y. I'm going to plug in for y. That's going to leave me x's in my equation. I'll have 15x minus 5. And then instead of a y, I'll have 2x plus 3 equals 30. And that's that new equation I was talking about. What?
You can combine electrons.
We are. That's exactly right. It just becomes a multi-step equation. Now let me ask you a question. Why did I insert parentheses?
Multiply.
I had to multiply 5 times what? Y, the whole thing. So multiply it by 2x and by 3, right? What property did I form right here? That's right. Let's do it. So 15x minus 10x minus 15 is equal to 30. And don't make the same mistake that we commonly make. If they're on the same side, I don't do opposites. It just tells me 15x minus 10x. That's 5x. I'm not going to do opposites if they're on the same side. I'm just going to combine my terms. Alright, I'm solving for x. Add 15 to both sides. 5 by 5. So x is 9. Now, since both variables did not cancel out, and I actually got a value for a variable, I got x is 9, then I know x is 9 and I have a consistent independent system. Remember, both variables have to cancel out to get an inconsistent system, no solution, or a consistent dependent system with inconsistent. What would be the best place to plug in this x is 9 to find y? Into equation 1 or into equation 2?
2, because you just solved.
It's straightforward, isn't it? Because if I know that x is 9, all I have to do is plug it there. Now, could I do it up here? Sure. This one looks a little easier, so I'll have y 2 times 9 plus 3. I already have the y isolated. So again, let me ask you, why is this better than the graphing method?
Because it's more accurate.
It is. And look how big. I mean, can you imagine? 921, I would have had to make a really large graph. Probably use a scale of 3 instead of a scale of 1 or something like that, right?
And then be completely.
Why did I say scale of 3, John?
Scale of 3.
Why did I say I would have to use a scale of 3?
Because they'll both divide by 3.
They're both divided by 3. So, and I would have known that when I started. Not necessarily. I could have looked here and said my x-intercept was what, guys? C over A. What would be my x-intercept if I had been graphing this? 2. What would have been my y-intercept? -6. Good. What would be my slope? Negative A over B. What would that reduce to?
Negative 3 points.
Is it negative?
Positive.
Yeah. Alright, so that's standard form. Alright, let's look at slope intercept. We're just reviewing graphing for just a moment. What would be the slope?
2 over 1.
Good. What would be the x-intercept?
Negative 3 over 2.
Negative 2 over 2. What would be the y-intercept? 3. So I'm not sure that I would come up with a scale of 3. Looking at all that. You might know. Alright, this is one for you to try. Can you tell me what kind of solution, and is this going to be, or what kind of system, is this going to be an inconsistent, a consistent independent, a consistent dependent? What
It's
kind
gotta
of,
be consistent, independent.
independent, how do you know?
Because it'll cross. That's a horizontal line. That's not.
And this is not, right, and this is also not vertical, so I know they're not gonna be parallel, and I know they're not going to be intersecting, right, or perpendicular, I should say. So, I know that, and I also know the solution, I also know that this is not the same line as that, I think that's where I was trying to get to. This is not the same line as that. And so y is 5, and I have a consistent independent system. So I'm gonna let you guys take a moment and find x. Alright, you did a good job, all you had to do, because this is, now this is the easiest kind, because if you have a vertical or horizontal line like you do here, all you do is sub in. And so she found 25, subtracted 25, divided by 2, negative 5.5. Again, better with an algebraic method like substitution or elimination than it would be with graphing, because, you know, you're going to be estimating, even though it's pretty easy to estimate with 5.5. Alright, what form is the second equation in? Is the second equation in? None. Right? It's not slope-intercept or anything, but the first step has been done for us because x has been isolated. Where do we substitute this in?
For the y?
It tells us x.
Oh.
So
my
we
bad.
substitute into the other equation for x. Alright, so we're going to have y's left when we do. So you're going to substitute in and solve for y, and then plug back in and find x.
Instead of just one.
Alright, good job. They substituted in. Remember this, and this is very commonly missed, that if like terms are on the same side, that you just put them together. They had different signs, so he subtracted, then added 18, and then did get a very large number in 98. The easiest place to plug that y back in was here, and found that to be 55. So again, that would be very tough with the graphing method at 55, 98. Huge. So an algebraic method is best. Alright, so let's look at this one. This problem does not have a vertical line, does not have a horizontal line, and x or y, neither has already been solved for. But if you look at equation 1, it would be pretty simple to get y by itself, would it not?
Yes.
Now, I'm not saying that's the only way this problem can be done. You can solve for x or y with either one.
But how?
In order to get y by itself, it would be just like putting this equation, which is now in standard form, into slope-intercept. So, what would I do? You tell me. How would I
Subtract
solve for
3x.
y? I would do what?
Subtract 3x.
Subtract 3x.
So it's already 214.
Okay, does anybody have a question? So now it looks just like the problem you guys just worked. This is y. This is the first equation. So where do I plug this in now? To the second equation. Make sure, this is what I said earlier, and I know you didn't have enough information yet to fully understand. Guys, look, this is the first equation. Don't plug it back in for itself. You'll get a consistent dependent system. So plug this into the other equation. So that'll be 5x minus 7. Take that y out. Because in the place of y, we're going to put what y is equal to. And now we'll solve for x. Property, watch your signs. Combine like terms. These are on the same side, so don't do opposites, just combine like terms. Add 28 to both sides. Divide by 26. 39 over 26, 13 will go into 39 3 times, 13 will go into 26 2 times. And so I have a consistent independent system where x is 1.5, 1.5, or 3/2. Now, what would be the best place to plug that 3/2 or that 1.5 in to find y? Would you plug it in here, or here for x, or over here? Right here would be the easiest, wouldn't it? Any of them would work, because y is already isolated right by itself. And so we'll say y equals -3 times 1.5, or 3/2 plus 4. So -1/2, or -0.5. I gave fractions and decimals. It doesn't matter how you write it. You can do 1.5 and -1/2, or you can do 1.5 and -0.5, however you want to write that. The only thing that we did differently on this example than we did on the previous ones is that we had to get y by itself before we started. That part had not been done for us. Does that make sense? Okay, somebody explain to me why we chose equation 1 to solve for y. We could have chosen either equation to solve for x or y, but why did we pick the first equation to solve for y?
Because we used the second equation or something.
Why didn't I say I'm going to solve for x on this equation?
Because you had to get y by itself.
Okay, why didn't I choose this one and get y by itself here? Isn't a 1y easier to solve for than a -7? So when it's just a 1y or a 1x, pick that one, because that's the easiest one to solve for. Because this was the simplest, that's why we picked it. We could have isolated this x, and hey, we had a lot of fractions in there, but it still would have worked. Alright, what do you say would be the easiest to solve for here? X or y in the first equation or the second equation?
Second equation.
Second.
Yeah, because it's a 1x, right? So we'll take this equation and what would we do to get x by itself?
We'd subtract 3y.
We would. So x would be equal to a -3y plus 4. We can't combine those because they're not like terms. Does that make sense?
Yes.
Where would we substitute this in? Since this is the second equation, we would sub this into the first for x. Just like subbing into a ball game. I'm going to take that x out and put this -3y plus 4, which is equal to it, in its place. And then solve for y. I'm not. Alright, do the distributive property. Combine like terms. So would you guys say the substitution or elimination method is easier?
Substitution.
Okay. Look at this answer, what it's going to be. Makes me feel like I did something wrong. But that's it. It's much better than graphing. Where would be the easiest place to plug this back in to find x?
The other way.
Gotta look. Would it be easier to plug it in here or here or here? If you'll plug it into that equation where you solve for that other variable. Alright, let me ask you this. How will I know if my answer is right?
So you
That should work in both of them.
It should work in both of them. What if it works in one of them? Do I stop and accept that? No, because the other day I had to do the first block. Has Bella?
Yeah.